Okay, so on number 1, it says the horizontal asymptote is y equals 0. So if it's y equals 0, it has to be bigger on the bottom. So when you FOIL at the top, this is x squared times x to the 7, or 7, it gives you x to the k plus 2. So k plus 2 has to be smaller than 5. So k plus 2 has to be less than 5. Then k has to be smaller than, when I subtract that, has to be smaller than 3. Can't equal 3, has to be smaller. So you really had to figure out like how to make that exponent be 4 or less, essentially. So k being 2 would make that exponent in the numerator be 4. If it had other options of 1 or 0, you would have not been able to like pick the right answer. So that's why the smallest one was 2. All right, on 2, when we distribute the numerator, the leading coefficient becomes 2x cubed in the numerator. Same on the bottom, it distribute and you get 6x cubed. So this reduces to being 1/3, and note that it's both same. So 1/3, if it's both same degree, both same, are and behavior would be following the horizontal asymptote of 1/3. So it should have been D. Yeah. Okay, I'm so glad I could help you with that. On 3, I thought 3 was kind of tricky to know exactly what to do. In these types of questions that say which of the following are true, I would suggest you look at how your answer choices are written out. So looking at the answer choices, at least on A and B, it's trying to make them have one fraction. So to make this be one fraction, I have to get common denominators. So you're multiplying the left one by x minus 1, and then the right one by x plus 3 to make the denominators match. So you have x minus 1 times x plus 3 in the bottom, and then we're distributing in the numerator. So we get 2x to the 4th minus 2x cubed, and then this one is minus 4 distributes. And the only one that matches that is A. But then if you did distribute the bottom, you'd have x cubed, or x squared, plus 2x minus 3. And looking at their degree difference, the numerator has a 2x to the 4th, denominator has x squared. This would 2x to the 4th over x squared simplifies to 2x squared. Another reason why it's A. I think that was tricky just if you didn't know how to get them to be one fraction. You might have picked B instead. Then looking at 4. Okay, on 4, we have a quotient, f over g. We know f is 6x cubed, blah, blah, blah. Slant asymptote is 2x minus 1. So f is in the numerator. The only parts we really care about are the leading coefficients of the numerator and the denominator and the slant asymptote. We haven't really discussed actually finding the equations of the slant asymptotes. In order for there to even be a slant asymptote, what does the ratio have to be? Big bottom, big top, both same. What do we think? Big top. So you have to make sure that the degree of the numerator is larger than the degree of the denominator. So the degree of by 1, because this is to the first power. So what would the degree of the denominator have to be then? 2. So we can already cancel out C and D. So degree 2. We already know G has to be degree 2. And then in order, what does the leading coefficient have to be to make 6 divided by something equal to? 3. I feel like a lot of these questions seem really intense, but once you get used to how the AP style questions are not quite so bad. Yes, sir.
So why didn't you just take the leading coefficient from x?
Because the end behaviors like slant asymptotes and horizontal asymptotes are really just dealing with the leading coefficient in the numerator and denominator. And like doing.
How do you figure out what g of x is?
So because there's a slant asymptote, the numerator's degree had to be bigger than the denominator. So the numerator was 3. And I see that the slant asymptote had a degree of 1. So the difference between numerator and denominator had to be 1, the degrees. And then their coefficients had to be a fraction that gave me 2. All right, then looking at 5. So on 5, we got h of x, describe the end behavior. This one was another one I kind of had to like zoom way in on. We got 2x to the 5th over 3x squared. So again, we're just caring about the leading coefficients. So I only care about the 2x to the 5th and the 3x squared. Reduce that. And you have 2x to the 3 over 3. So this just looks like a cubic polynomial who is positive. So on the right side, it's going up. And on the left side, it'd be going down. So as the x's are increasing without bound, the y's, or h, I think is what it used, should have been also increasing without bound. When the x's were decreasing without bound, the y should have been decreasing, which I think is A. X increasing, h increasing, x decreasing, h decreasing. Yeah, A. And last but not least, now you, I think, also maybe know why in 1A we started with polynomials and end behaviors and talk about increasing and decreasing, because then it's like flowing into this section pretty well, like to talk about their end behaviors. Okay, on 6. A lot of you got this wrong because you did not read, so please read. Reading is fundamental. So polynomial has 3 distinct zeros. That means it's like, for example, x minus 3, x plus 1, and x minus 2. That just means no multiplicity of anything. So they were all just different zeros. What degree would that be if there's 3 distinct zeros? Cubed, or third. The leading coefficient's positive. So the numerator is positive x cubed. Then the denominator has exactly 1 0 with a multiplicity of 3. So that's like x minus 1 cubed or something like that. So its multiplicity of 3 meant that root was repeating 3 times. So what was its degree? Also 3. So when we stack numerator over denominator, again, we only care about the leading coefficients. So the numerator would have been positive x cubed and the denominator would have been negative x cubed, which is what? Big top, big bottom, or both same? So this is both same. And when it's both same, we reduce them and we're left with -1 or negative something. We don't really know if it's 1 or if it's 2 or whatever. We just know that's negative. So then looking at the asymptote, whatever the leading coefficient was, it just had to be negative. And that's what the asymptote was at. Okay. Any questions from that? All right, let's get our notes out. Oh no, my apple. We are doing 1.8 today. I think 1.8 is probably more new things than 1.7 was. Just like new in like the construct of how the questions are being asked. So 1.8 is dealing with zeros and actually vertical asymptotes. But we're going to be doing the zeros and vertical asymptotes as inequalities and figuring out where the rational function would be positive or negative. So that's why I think this is kind of new for you. So rational function has no common factors. So if there's no common factors between g and h, that means that there's no wholes. All Remember, wholes are if I can cancel from the numerator and the denominator. Then the zeros of the entire function come from, not in highlighter. The zeros from the entire function come from the numerator. So the zeros, aka the x-intercepts, we set the numerator equal to 0. Where a function is undefined is when the denominator would be 0, because you can't take 30 parts and divide them into nothing, right? I can't take 30 things and divide them into no groups. They have to have some kind of division going into them. So the denominator, if we set the denominator equal to 0, is undefined. And really, if you remember correctly, undefined really means that there is a vertical asymptote there. And I always abbreviate vertical asymptote VA. So when we're solving rational inequalities, you need to identify both the zeros and the undefined values. So we're finding both the x-intercepts and the vertical asymptotes. Because if we're doing inequalities, we're saying this rational function, where is it positive or where is it negative or where does it equal 0? And the vertical asymptotes are kind of like, here, let's actually look at a graph. I have a graph right here. So if we're looking at, this is a rational function, and it has 2 vertical asymptotes. I think I actually want to do this example first. So first I want to identify the vertical asymptotes. This is example 7 at the bottom of the next page. So I want to identify the vertical asymptotes and the x-intercepts. So I see these little dashed lines, but even if the dashed lines weren't there, look at how the function is splitting off. There has to be a vertical asymptote at x equals -3 is a vertical asymptote. And where's the other vertical asymptote? 3. And this is another reason at the door, when you guys have held your hand up straight in the air, when I said, show me the graph of y equals x, I told you no. Because a line going straight up in the air is x equals number. Right? So that is not y equals x. And then horizontal line, so you're like, go x, but y. Y equals is this way, like a valley girl. You're like, y. So y equals is a horizontal line. So we have a horizontal asymptote. We don't really care about it, but so much, but let's identify it just, so we know all the parts. So we have a horizontal asymptote at 1. Where are the zeros? Yes, -1 and 2. So we have a 0 at x equals -1 and at x equals 2. I like to write zeros as ordered pairs just because x equals to me as a vertical line, not a point. But you do you, boo. So now we can actually answer these questions. We need to think about where's the function on A, where's the function less than or equal to 0? So really that's saying, where is it negative or 0? Negative looks like it's here. So this should be pretty easy to complete. Where is it approaching? It's not going x to -infinity. What x value is it getting really close to but not crossing? -3. So we have -3 up until the x-intercept of -1. And then pick back up at 2, and then it's approaching the other vertical asymptote at 3. So this is a vertical asymptote, and this is 0. This was a vertical asymptote. This was a 0. Okay, so now we have to figure out parentheses or brackets. Can you ever touch a vertical asymptote? No, remember asymptotes are like force fields. So if you're getting, or like electric fence, if you're getting really close to -3, which is the vertical asymptote, you don't want to touch it or else you're going to get shocked. So it should get a parenthesis because it cannot equal -3. So we can't equal. So it should have parentheses. In this situation, we had less than or equals to. Can we equal x-intercepts? Yes. So we are going to put brackets because we can equal x-intercepts. And this question had a less than or equals to. So I want you to try to do B. Notice no equals to on B. So if there's no equals to on B, are we going to have any brackets in the entire problem? No, everything should be all completely parentheses. This whole function's f of x. A rational function's like that whole entire graph. Okay, so going from left to right when you do the interval notation, we have from -infinity up until the vertical asymptote. And then pick back up on this little swoop that's positive. And then from the vertical asymptote to positive infinity.
Why is it infinity instead of 1? Because isn't it going against the...
Those are the y values. Y is 1. But the x, as x is going to positive infinity, the y's are approaching 1 forever, but it's still, the x's are always going to be, as x is getting bigger, the y's will stay positive.
And why is there -1?
Because then that little interval, the graph was above the x-axis. So like from -1 to 2, it was positive.
Why aren't the brackets on?
Because it was a greater than not equals to. If it had said greater than equals to, then you would have had brackets on those two. At first I put brackets and I was like, oh shoot, wait a second, there's not an equals to sign. Okay, and I think C is maybe easy, maybe tricky. Try to do C. I don't know your life. All right, where is it bigger than 1? Bigger than 1. Yeah, -infinity to -3 and 3 to infinity. They don't get brackets, even though there is a less than or greater than or equal to. Why don't these have brackets? Right, they're vertical asymptotes, so you can't equal them.
Wait, isn't it 1 on the line?
Excuse me?
Wait, when it says vertical equals y, it's saying the 1.
So where are the y's bigger than 1?
Okay.
Is everything above y equals 1. All right, let's flip back in time and solve with the equation. I feel like this is doing the same thing, you just can't see the graph. But I felt like at least seeing like what a rational function is supposed to look like might help you understand like why I have x-intercepts and zeros. So when we're solving, just like looking at an inequality, it's like checking the chunks again. So anytime we're solving inequalities, we're checking the chunks. It's like a game show. Check the chunks. So checking the chunks, you have to figure out how to make the inequality have one side be 0. I'm probably not going to give you any inequalities, at least not yet, that are not already one side being 0. But one side has to be 0. So looking at example 1, is one side 0? Yeah, okay, good. Then you have to make sure that it's a single rational function. So example 1 and 2 are a single rational function. I don't think I have any that are not, but if they weren't a single rational function, you have to get common denominators and make them be one fraction. Then we're setting the numerator equal to 0 and the denominator equal to, that's an N, denominator equal to 0. So the numerator equal to 0, what is that going to give you? X-intercepts or vertical asymptotes? X-intercepts. We can say 0 divided by number is 0, but number divided by 0 is like even Thanos, when he did the Thanos snap, there's still little particles of people floating around in the movie. Although that movie's getting a little outdated. I don't know if you guys have seen Avengers Endgame. This gives me a vertical asymptote. So right now, on example 1, set up a number line. We're setting the numerator equal to 0. So numerator equals to 0, what is that going to give you? 2. This is a 0 or an x-intercept. Looking at my inequality sign, it's a greater than or equals to. So can I fill in the circle or is it open circle? Fill in. I can equal x-intercepts. Then looking at the bottom, we have what? -6 and 3. So what are these? And vertical asymptotes, can we equal them? No, so that's why they're going to be open circles. All right, you still have the regions. So we want to try to check our regions. Rational inequalities are more difficult than polynomial inequalities because they don't just do like the kiss-cross thing. Sometimes they'll like bounce back. They kind of move the way you think they should move, but I would just check all of them to be safe. So what's a number in interval 1? Okay. So plugging in -7. Again, I don't care what the value is equal to. I just care about the sign. So if I care about the sign, -7 minus 2, yes, it is -9, but I just care whether it's positive or negative. Then -7 plus 6, is that positive or negative? Negative. And then -7 minus 3, negative, which gives me a negative over a positive. Negative divided by a positive is negative. Is that bigger than 0? No. Again, we're checking with what the inequality is asking us for. So are we going to shade region 1? No. Then region 2. What's an easy number to plug in region 2? Marielle and Allie, stop. What's an easy number to plug in for region 2? 0 would be easy. So 0, we got negative over positive times negative. So that gives me a negative over a negative. So negative divided by negative equals a positive. So am I shading? Yes. That's a long interval to shade. All right, plugging in for interval 3. 2.5. That's fun. That's going to be positive on the top because 2.5 minus 2. And then 2.5 plus 6, positive. 2.5 minus 3, negative. So you have a positive over a negative. Negative. Are we shading? No. And bigger than 3 would be 6. Okay. And we get 6 minus 2 is positive. 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 Is that shading? Yes, all positives. Okay, so our solution, we just look at what we shaded. We go from negative 6 to 2 and 3 to infinity. What parenthesis or bracket, what's going to happen on negative 6? Parenthesis, because it had an open circle. On 2, it would be bracket. 3, parenthesis. Infinity, always a parenthesis. Try to do 2. What should you maybe do first on this one? Factor. Our favorite F word. So when we factor this, you get in the bottom x minus 5 times x minus 5. It's kind of a good idea when you have a repeated factor to write it as x minus 5 squared, because this tells you when you're checking the chunks that this number is whatever we plug into the denominator, what sign will it be? Positive, because even a negative number squared is positive. So no matter what we substitute into the denominator, this is always going to be positive. So it just makes plugging it in a little easier. That one, well, in this situation, all of the circles are open because it's a less than and not equals to. But yeah, that would have, because it's in the denominator, been open anyways. Mm-hmm. But like when I'm thinking like when I'm checking the chunks and plugging into the denominator, I don't even have to think about it. It's just going to be a positive. So even though these are x-intercepts, and this is a vertical asymptote, they are all open circles. Why are they all open circles? Yes. That's more, it kind of does that, but that's a polynomial trick.
Oh,
not a rational function. Rational functions, like, these are like following at 5 because it has an even multiplicity, the rational. So remember, 5 is like like this. But because it has an even multiplicity on either side of that vertical asymptote, we're going to follow either both going up or both going down. Okay, so plugging in 1, 2. For first interval, I think I'll plug in -3. Negative times negative, always a positive on the bottom. This is going to be positive. Positive is not less than 0. No shading. Then I'll plug in 0 because that's an easy one. Negative times positive over positive. Is that smaller than 0? Yes. Then maybe plug in 3. Positive, positive. Always a positive in the bottom. No shade. And like I was saying to Jordan, at that vertical asymptote, because it has an even exponent, the end behavior on either side is going to match. Like the signs are going to match on either side of 5. But you can also just check if you're not sure about that rule. You have positive times positive over positive. We're not shading again. So the only place we had shading was -2 to 2. How did we do? Well, you know? Okay. I was going to skip example 3, but 3 is kind of, I feel like some of you won't know what to do. Yeah.
So why is the x minus 5 squared always positive?
Because no matter what number, I'm saying like when I'm checking the chunks into there, it's always going to be positive because like even if it was like -7, what's -7 squared? It's always positive, right? So a -100 squared, 10,000, 100,000, whatever it is, it's always going to be positive because you're doing negative number times negative number gives you positive number. So like that, you don't have to know that it's always positive. It's just for me, like if I can not think too hard, I like that. So I'm like, okay, I'm plugging in -3 into the bottom. That's -8, but that is being squared, so it's actually positive. So I'm just trying to not think very hard. Okay, so 3 I think is pretty easy, but I just don't know. It's different looking than the other ones that we've done. So try to set up your number line. What would the number line have to be on 3? Is there an x-intercept? No, there's no x value in the no variable in the numerator. So there's no x-intercept. Is there a vertical asymptote? Yeah, it's at 3. So we really only have to check 2 sides of this, like a 1, 2, left and right. Okay, so checking on the left, -4 or 0. It's positive or negative?
Negative.
And then this one, plug in 4, we're going to get positive, and we wanted positives. Wow, that was a little too easy. Let's try to do, I think the last one, we'll do 5 and 6. 5 is tricky, and 6 is a little tricky too. I don't think it factors. It's already factored.
Just double checking.
while you try to do that one, I'll pass out your classroom. Well, I almost passed out my calculus classwork too. I want to integrate those parts. Okay, so remember this has a greater than or equals to, so our x-intercept should have filled in circles. And the vertical asymptote should have open circles. Okay, checking -3, I have negative, and then this one is always going to be positive because it's squared again. So if you want to set up your little fractions for when you're checking, every single one of these is going to have that second parentheses be a positive. Again, it doesn't really matter. It's just like me being lazy and trying to not have to think too hard. So when I'm plugging in -3, I have negative over negative, which is a positive. And what did I wanted it to be bigger than 0. I wanted a positive. So I'm shading over here. Okay, plugging in 0. 0, I have negative over negative, which is another positive. So I would shade there too. Okay, 1.5. Awkward to plug in. 1.5 minus 1 is positive. 1.5 minus 2 is negative. So I have a positive over a negative. Am I shading? Near. And then positive, positive. It's positive. Am I shading? Yes. Are there questions about how we got the shading? So I want to make sure we address that before we do the actual interval. As long as you have the circles filled in correctly, you should be able to write this interval notation correctly. So what is the farthest left thing that we have shaded? Negative infinity. And then, here's what I don't want to see you do. Don't write this. Why is this wrong? Yeah, this is redundant. If I go from negative infinity to -2 and I can equal -2, and then I can equal -2 to 1, I didn't need to break them apart. The graph is filled in this whole interval up until 1. So don't do this. Because if you have brackets around those, they should just be lumped into the whole interval from negative infinity to 1. This is like unnecessary breaking apartage because there wasn't a break in the graph. It was a filled in negative 2. It wasn't an open circle. And then 2 to infinity. That's why I wanted to do 5. That was a little tricky. Questions on that one? Lucy has scrunched face. Questions? Okay, just resting scrunch face. Let's try to do example 6. This is our last one. I bet you can do it. Confirm with your neighborhood. You got a 50-50 shot. I'll get this copy this way. Okay, so we got positive always in the numerator because it's always 1, and positive in the denominator always because it's squared. So is there anywhere where this is going to be less than 0? No, and it doesn't even equal 0. So this is no solution. It's never going to be negative. Okay, on the classwork, we have kind of a lot. Oh, sorry. Yes. We're going to do 1, 3. It's kind of an awkward amount of numbers, so you might want to circle the questions. We got 1, 3, 5, 6. On 6, we'll test your factoring skills. 7, 9. 10. So on the front, we got 1, 3, 5, 6, 7, 9, and 10. Flip it over. I don't know why it printed this way. And I think our last one will be 15. I should have probably done more, but I feel like that was already kind of a lot. We'll see. Maybe you guys will fly through it.